Okay, let's dive in. Picture this. You're inside the Red Pyramid in Egypt, thousands of years old. Just incredible.
Yeah, a real marvel.
But there's this smell. It's been talked about for ages.
Not dust, right? Something else.
Exactly. People used to say bats, but, well, there's no sign of them deep inside.
No evidence, nope. But the smell itself, that seems real. Persistent.
And the recurring idea, the one we're exploring today based on work by at the Land of Chem and Jeffrey Drum, is that it's ammonia.
Right, and if you accept that premise, just for a moment, that the smell is ammonia.
Then things get really interesting, because
How? How does ammonia, a gas, seep out of solid granite blocks?
yeah, granite's not exactly a sponge, is it?
Not at all. So this deep dive, we're looking at a fascinating, maybe speculative, but really compelling theory.
Connecting ancient Egypt and, believe it or not, modern industrial chemistry. Get ready for some aha moments.
So the central question, if it is ammonia coming from the rock itself, what could possibly force it in there?
And this is where Jeffrey Drum's idea comes in. Pressure.
Pressure. Okay. Natural force. How does that connect to the pyramid itself?
Well, look at the design. The chambers inside, they don't have flat ceilings.
No, they're angled, like a rooftop meeting at a peak.
Exactly. So imagine gas being forced upwards into that space. What happens?
It gets compressed, right? Squeezed into a smaller and smaller area. Higher pressure.
Okay, so the shape helps, but where does the initial upward force come from?
This is where you have to look outside the pyramid to the environment, specifically the Nile
Ah, the Nile. Always
Yeah.
crucial in Egypt.
and the entrance passage. There's that weird 90-degree bend. Some call it the toilet door.
Yeah.
Uh,
Not exactly for privacy, Drum suggests.
No, he thinks it's functional, designed to allow the entrance shaft to be deliberately flooded.
Flooded with Nile water. But
Hmm.
wouldn't they want to keep water out of a pharaoh's tomb?
You'd absolutely think so. It seems totally counterintuitive.
There's always a but.
But, get this, during the annual inundation, the Nile floodwaters actually rose higher than the pyramid's entrance level.
Seriously. Higher than the door.
Apparently so.
Yeah.
Which makes you ask, why build the entrance so low if you're trying to keep floods out?
Unless you weren't. Unless you actually wanted the water to go in, maybe in a controlled way.
Precisely. Control flooding.
Yeah.
Use the immense weight of the Nile's floodwater in that entrance shaft.
To create hydrostatic pressure.
Exactly. Pushing upwards, forcing any gases already inside the pyramid up into those angled chambers.
Compressing them further. Okay, I see the pressure mechanism now.
Yeah.
Water pressure from the Nile, focused by the architecture.
The plausible mechanism for generating significant pressure inside.
But pressure alone doesn't make ammonia. Where does the chemistry come in?
This is the leap. Jeffrey Drum noticed a striking similarity between the pyramid's internal layout, the sequence of chambers, and a modern industrial process.
You mean the Haber process?
The very same, the Haber-Bosch process, yeah. The way we make almost all ammonia today for fertilizers and stuff.
Wow. Okay, so break down the Haber process simply for us. What's the core idea?
Well, in essence, it uses high pressure and catalysts, usually in 3 main stages or chambers, to force nitrogen and hydrogen gas to combine into ammonia.
3 chambers, pressure, starting to sound familiar.
It is. Let's simplify. Chamber 1. You need hydrogen. You might start with methane, natural gas, CH. Heat it, maybe with water, under pressure.
And that breaks the methane apart.
Right. It releases the hydrogen, H. The carbon reacts with oxygen, often from the water, making carbon dioxide. So out comes stage 1, hydrogen gas mixed with Keo.
Okay, hydrogen unlocked. What's chamber 2 for?
Chamber 2 is where you introduce nitrogen. The easiest source is just air. This is mostly nitrogen.
So you pump air in.
Pump air in. Now you have hydrogen, Keo, and nitrogen, plus other air gases. Under pressure, the Keo can be dissolved in water, kind of scrubbed out.
Like bubbles in soda, yeah. So you remove the Keo.
And you're left primarily with a mix of nitrogen and hydrogen, still under pressure.
Got it. Hydrogen from stage 1, nitrogen from stage 2, now stage 3.
Stage 3 is the finale. You apply maybe even more pressure, often with a catalyst, and that forces the nitrogen, N, and hydrogen, H, to bond.
N plus 3H becomes 2NH, ammonia.
Exactly. Ammonia is formed, and because it dissolves well in water, you can often collect it that way. So it's basically a 3-chamber, pressure-driven system, often involving water.
Hold on. 3 pressure chambers in Haber-Bosch, 3 main internal chambers in the Red Pyramid.
The parallels are suggestive, aren't they?
Suggestive is putting it mildly. It's not a perfect one-to-one map, obviously, but the sequence.
And think about the layout vertically. In many Haber process setups, that final reaction chamber where the ammonia actually forms is often elevated.
Elevated. And in the red pyramid
The innermost chamber, the third main chamber, the one where people consistently report that ammonia smell.
is higher up than the first two chambers.
It is indeed.
Whoa! So that pervasive smell in the highest chamber could actually be residual ammonia, left over from the final stage of this ancient chemical reaction.
That's the core of the speculation. The smell is the lingering evidence of ammonia production, driven by water pressure, happening right there in that top chamber.
Connecting the smell, the architecture, the Nile floods, and modern chemistry. It's quite a thread.
It really is. And again, we have to credit at the Wendorf Chem for really developing this line of thought, and Jeffrey Drum for these specific insights,
Yeah.
linking it to the Haber process and the pressure mechanism.
Absolutely. And if you listening want to go deeper, because we've really just sketched the outline here, you should definitely check out thelandofchem.com.
Yeah, Jeffrey Drum's work is detailed there. You can see the diagrams, the full arguments. It's worth exploring.
So let's just pause on that aha moment. The red pyramid. Not just a tomb, potentially, but a chemical plant.
A sophisticated water-powered chemical reactor designed perhaps thousands of years ago to produce ammonia. It's a mind-bending possibility.
It completely reframes how you might look at it, doesn't it? Could it have had a dual purpose? Pharaoh's resting place and chemical facility?
Or maybe his primary purpose wasn't burial at all. It opens up so many questions.
And it makes you wonder, if this theory holds any water, what other secrets are hiding in plain sight in ancient structures? What happens if we start looking at them not just as tombs or temples, but through the lens of engineering, chemistry, physics?
It encourages that multidisciplinary view, doesn't it? Looking beyond the traditional interpretations.
Definitely food for thought, a really provocative idea, linking the distant past to our present in a totally unexpected way. Go check out the sources, mull it over. What do you think?